Anytime you set the upper control limit and the lower control limit on a quality control chart, you're going to be taking a risk. What is that risk? It's essentially the risk of being wrong. That's the risk that's mentioned here in this problem. Let's take a look. Suppose a manager must construct either a mean chart with no variation or a P chart to monitor some process. When the process is in control, notice that. Nothing wrong with the process. The manager wants only 1.92% of the samples to fall outside these limits. That's what I mean by being wrong. Okay, so, well, let's stop here for a second before we go any further with this problem and talk about that. What's being said here? When the process is in control, the manager wants a little bit less than 2% of the samples to fall outside the limits. And you're probably thinking, well, wait a minute, if the process is in control, I thought that meant that things fell inside the limits. Not always. Now, it helps me to draw a picture. I'm going to draw a control chart, but not how you usually look at one. Usually we look at control charts running from left to right. This is a control chart that's been rotated. I just took one and rotated it so that it's going up and down, but that's the lower control limit. This is the mean of the process, right, the center of it, and that's the upper control limit. Now, why did I draw it in such a strange fashion? Because it makes it easier to sketch something that's a little bit more complicated. That is the normal distribution that represents the natural variation in the samples from this process. Okay, so I tried to draw a bell-shaped curve. Oh, right, because the process varies naturally. So we assume that variation that we observe then among samples that we pull from the process to be normally distributed. Now, here's the risk. This distribution represents things being normal. I mean, this happens normally, nothing's wrong. We have created a chart in which we said, no, we don't want to see anything less than that. No, we don't want to see anything more than that, or we will assume that something's wrong. We actually amputated at least a small part of what naturally happens anyway. The entire area of this curve represents what naturally happens with samples anyway. Nothing's wrong. Okay, so we create a chart in which to plot the samples. We're actually cutting out part of what naturally happens anyway. That is known as a, oops, type 1 error. When a sample falls outside the limits, when in fact nothing's wrong, that's known as a type 1 error, also known as the producer's risk. Why the producer's risk? Because think about how we use these charts. Okay, you take a sample and you calculate it and you plot it and it's outside the limits. Think of how we use the charts. You say, oh, whoa, that's outside the limits. Stop the process. Stop the process. Tear down the machine. There must be a problem. Okay, well, in this particular case, if it was a type 1 error, no, there's not a problem. Okay, because not very often, but sometimes that happens. The samples vary that much. Oh, so you'll tear down the machine and you won't find any problem, right? And you were wrong to actually stop the process. Okay, that's your risk as the producer. Oh, that's actually the 1.92%. That's what the manager's saying. Okay, well then find a way to place these limits such that that only happens a little bit less than 2% of the time, 1.92%. Now, find a way to place these limits. Oh, maybe we should finish reading the question. What is the z-value that the manager should use when calculating the limits of this chart? Right. At the beginning it said mean chart with no variation or P chart. Notice that these are the charts that when you look at the formula for upper control limit and lower control limit, there's this z-value in the formula. This is, in picking a value for z, this is how we can control the producer's risk. Okay, you say, oh, all right, how so? Well, first off, let's look at what was actually asked. 1.92%. Okay, what this means is, if you want to relate it to this illustration, is that wherever these borders were put, if they were placed correctly, 1.92% of the overall shape would have been colored in yellow, has been excluded. Oh, now I need to be careful because we're going to work in the decimal form of proportion. 1.92% is 0.0192. Okay, got it. Now, that is the total amount that's in yellow. So that includes both tails. They're identical. If we take that and we divide it by 2, I get 0.0096. And we're saying, okay, fine. Why do I care? 0.0096. That means that, for instance, this tail right here, that's exactly how much should be caught outside of the upper control limit, and it's symmetrical, so the same thing here. Now, you say, all right, fine, but what this has got to do with the z value? Oh, well, wait. Gee, you know, I can see the proportions, but I need a z value to put in the formula to make sure that that proportion happens. You know, I really wish I had this table that, like, for a certain area of the curve, it would tell me the z value that corresponded to that would make sure that that happened. You know, I really wish I had some kind of table that related the area of the curve to the z value. Actually, I do have that table. That, by definition, is the z table. Here's the z-table we're accustomed to working with in quality control. That's exactly what it's telling me. It's like, for if you look at the center of the table, for various areas in the curve, what is the corresponding z-value? Oh, so I can use this table to track down the z-value I should be using in this case. I have to be careful, though. All z-tables will tell you exactly what area they're talking about. And notice that this z-table is reporting the area between the center of the curve and, you know, in our case, what is essentially the limit where we cut it. Now, what I had just determined was that 0.0096, that's how much of the curve should be here. But what I really need to know is then, well, how much of the curve should be here? Because that's what I could look up in the table. Well, that's not hard. The curve is symmetrical, right? So from this point on either side is 1/2. So if I said 0.5 minus 0.0096, just a little bit of scratch work, 0.4904, there, that would reveal how much is right in here, 0.4904. You say, all right, fine. Then what? Look for 0.4904 here in the body of the table. Look for the number that's closest to 0.4904. 0.4904, 0.4925, 0.4932. It's going to be pretty low. 0.494. No, that's 0.4904. 0.4904, 0.4904. There it is, just exactly. I don't have to look at what's closest. 0.4904. Now wait. How do I find out what z value is associated with that? Trace the row that it's on. There's the first 2 digits. A z of 2.3. 2.3 what? Trace up. What column are we in? 0.04? Then you can assemble the z-score because it would be the row 2.3, the column 4. There it is right there. That's the z that you should use. Got to remember that. Z equals 2.34, right? I got that by looking up 0.4904 on the table. That's the z that it belongs to, so to speak, so that when you are using the formula for the upper control limit and the lower control limit and you put 2.34 in for the z value, it's going to place the borders such that 1.92% of that natural curve is actually then excluded or outside of those limits.